this lesson is for my honors integrated 1. This will be lesson 19.4. I hope everyone is doing all right. I'm going to try and keep this a little simpler than what's in the book. And again, if you have any questions, please let me know through the Remind app or send me an email. And I want to just quickly, I keep saying, oh no, I want to quickly point out that we're in a very interesting situation with this teleschooling or whatever you would call it. And you want to make sure that when it's all said and done that we can say, hey, we did everything that we were supposed to do and we earned all the points that were out there were possible, so that we can, when it's all, when we're through with this, we can hopefully argue that we've earned credit for this class in this situation. So please make sure all the assignments are turned in. Make sure you've watched the videos. And let's just do what we need to do. And again, put ourselves in a position to say, hey, we earned our credit. Even though we weren't in the classroom, we still did what we needed to do. So anyways, today's lesson is going to be about right angles or perpendicular lines. And so let me just write down our goals today. So this is for 19.4. And our goals for this lesson are going to be define perpendicular, our second goal is going to be that we're going to talk about a perpendicular bisector of a segment. And by the way, perpendicular has a symbol. I'm just going to use that symbol instead of writing out the entire word. So we're gonna investigate perpendicular bisectors of segments. And we're also going to see the last idea, which I think is a pretty simple idea. I think it's actually very intuitive. And so we'll just call this one perpendicular lines and their angles. Alright, so I just want to see how much of the whiteboard I took up. Okay, very good, I got a bunch. Alright, so if I'm going too fast again, you can hit pause, go back and rewind it. The information that I'm telling you should be enough for you to answer the questions out of the book. So let's start off with our first goal, define perpendicular. So perpendicular literally means makes a right angle. So let's just define that. So perpendicular that's a symbol for perpendicular. It means they intersect and make right angles. The intersection, they intersect at 90 degrees. Or they make right angles. So that's pretty simple. So if I say the word perpendicular, you see that symbol, I'm saying to you without saying, we have a 90-degree angle. And whatever that leads to, we can actually use. So if it leads to maybe a problem about complementary angles, starting off with perpendicular, that could be something that you may see in the homework. You got an itchy nose. All right. So anyways, let me check off that first goal. The second goal is going to be to investigate the perpendicular bisectors of a segment. So our second goal. Alright, so the second goal is to investigate perpendicular bisectors of a segment. Remember, if I bisect something, I have cut it in half. Bisect means to cut in half. And so what I'm saying is when I cut my segment in half, I'm making a right angle. So an example of this could be something that looks like this. So here's my segment, and a perpendicular bisector would make a right angle to the segment, and it would cut the segment into two equal parts. These little marks again are how I show that this is the same as that. So this means that I have a, this is what a perpendicular bisector would be. Now, what we're going to investigate actually is we're going to look at this in two ways. So the first thing we're going to do, the first way that we're going to look at it, and I just have a feeling red's not going to show up well. The first thing we're going to look at is what does it mean if you're a point on the perpendicular bisector? What does that mean? So if I have a random point, we'll call this point M, and I have my segment AB that was perpendicularly bisected by this line L. And point M is just a random point on the perpendicular bisector. Now, there's going to be something that we can actually kind of reason our way through. Now, point M, the claim is if a point is on the perpendicular bisector of a segment, the claim is going to be that this point must be the same distance from point A as it is from point B. And the idea, to simply go through it, is that you're going to basically make, and it doesn't look this way, but you're basically going to make two identical right triangles when to complete this argument. And so, if we were to consider this length, we would know that it would be the same as that length. And if we were to consider this length for this triangle, it's the same as this length for this triangle. So, in actuality, if we were to just use the letters that we use for the Pythagorean theorem, we would see that this length right here would actually be a squared plus b squared, right? That's going to be the length from, and I'm sorry I'm writing a little bit small, that's going to be the length from M to A. Let me write this a little bit better. Is going to be a squared plus b squared. Now remember, this A length is the same as that A length. These lengths are the same because this segment got bisected by that line. And so these lengths are equal. So I can also say that the length from M to B is also equal to a squared plus b squared. So what this one result means is that if a point is on the perpendicular bisector of a segment, it must be equal distance to the endpoints, because a squared plus b squared is going to create the same length as a squared plus b squared. So that's one result from having a perpendicular bisector. So let's write that down. If a point is on a perpendicular bisector of a segment, then that point little okay. All right, so again, if you have a segment, gosh, I need to erase something here. I don't have as much whiteboard as I'm used to working with. But again, so if I have a segment, you know, and my endpoints are R and S, and I have a perpendicular bisector, and on this perpendicular bisector I have the point T, where I know that this line is cutting this segment into equal parts. I know that the length from R to T is going to be equal to the length of T to S, and that's one of the properties of a perpendicular bisector of a segment. So again, this point is the same distance from here as it is to here. That's one of the things. So as you look at the problems in the section, ask yourself, does this information help me answer it? So that's one of the three things that we're going to need to answer questions. I believe it's three things. I might have spoke too soon. All right, so we're going to talk about the converse of the statement. And the converse of the statement is going to be the following. If a point is equal distance from the endpoints of a segment, then we can conclude that that point must also be on the perpendicular bisector of the segment. Now, in the book, they have an argument using what's called an indirect proof. And an indirect proof means that you catch the situation in a lie. And it's kind of a hard method to argue and wrap your mind around. But basically, what it comes down to is you assume the false concept must be true. You work your way through the argument, and then what's going to happen is that there's going to be a contradiction, something that happens that cannot support your initial claim. And since that you assumed the false was going to be correct, and it turned out that the false assumption was incorrect, then that forces the correct assumption to be correct. So it's a really kind of a difficult thing to wrap your mind around as an argument technique, being that you guys are being introduced to argument styles. But let me just show you what we're going to use. I don't think that this is actually a very fair concept at this level, because again, you guys are learning to make arguments, and indirect proof and proof by contradiction is a very high level idea. So I'll just kind of show you what you need to understand. Okay, so let's start off with something that looks like this. Let's say that I have a segment that's, I don't know, endpoints are J and K, and up here I have some point N. And if we know that the length from N to J is the same as the length from N to K, we know that N itself must actually be on the line that cuts this segment in half, and must also be on the line also must be perpendicular. So the first thing was the point was on the line that was a perpendicular bisector, and we realized that it's the same distance from the endpoints. The converse of that, the backward statement, is if we know that a point is the same distance from the endpoint, that point must be on the perpendicular bisector of a segment. So I'm going to write the rule down, and hopefully this helps us understand how to use it. I'm going to see how long I've been rambling for. Okay, for about 15 minutes. I'm going to try and wrap it up here kind of quick. So in math, we have something what's called a biconditional statement, which means it's a statement that you can use in both ways. And this, I think that this is actually the best way to look at this. So it will say a point is on a perpendicular bisector of a segment, and we have this symbol in math that looks like this. And what it means is if and only if. So a point is on a perpendicular bisector of a segment if and only if that point, or a point, is equidistant from the segment's endpoints. And equidistant is actually a word. And so what's happening here is you have to figure out what you're starting out with. If you have a point that's on a perpendicular bisector of a segment, then you know that you have that it's the same length from the endpoints of the segment. If you have a point that's equidistant from the segment's endpoints, you know that that point must be on the perpendicular bisector of the segment. Excuse me. Having this means you get this, or having this means you get this. It's a statement that works two ways. And so, again, some of your problems, you start with this, you have to use this, or you start with this and you have to use this. So keep that in mind for those problems. I want to talk about my last concept, which is kind of a fairly easy concept to wrap our mind around. This is probably something you might want to hit pause and write down. All right. The last goal for this is going to be perpendicular lines and their angles. Okay, so if something is perpendicular, right here I have a right angle. Right? That's a symbol for a right angle. Because I have actually 4 sets of linear pairs. 1, 2, oh, do I have 4? 1, 2, 3, 4, yeah. So if this is 90 degrees, I know this angle and this angle must add up to 180 degrees. Therefore, this angle itself must be 90 degrees. Because these angles are vertical, I know that this must also be 90 degrees. And because these angles are vertical, I know that this angle must be 90 degrees. So the third goal, perpendicular lines and their angles. If lines are perpendicular, all their angles are 90 degrees. Not just one, all of them. So even in this picture, I know you're 90. You have to be 90 because you add up to 180, or vertical, you're equal, or you guys are linear pairs and you're 90, so you all must also be 90. So perpendicular lines make 4 right angles. That's our third goal. Perpendicular lines make 4 right angles. All right, so these are the main ideas. This statement and this statement, look at these for the homework. And broadly for the homework, there are some questions about constructions. Try to do them. If you don't do them, it's okay. I don't want to use the phrase "into the world," but I just did. So again, I hope everyone is doing okay. Again, let me know if you have any questions on anything. I will try my best to get back to you as soon as possible. And I'm going to upload this. And please, again, make sure that the assignments are turned in on time. I want to be able to say to my bosses, hey, look, my students did everything I asked while we were out. This has to count for a significant, significant portion of their grade. So, again, please make sure we're doing the work. And again, I hope everybody is doing okay. I will post the next video tomorrow. Have a good day.